Hello, today we are going to discuss the greatest angle of repose. What is that? Well, simply put, it is the greatest angle that you can put a slope at through which things will not fall off, they will not slide downhill. Of course, when something slides downhill, such as I'm creating here, it depends a lot on the friction, which we have just discussed. So that is what we're going to do today. But before I do my demonstration, let's take a look at the diagram. We have a hill, say that's on the side of a highway, which could be. We have a mass. It has a weight, which is a vector straight down. And it wants to slide down the hill with a force F, which is basically created by gravity. The angle of the slope is theta, and we're going to vary that to see what happens. If the angle of repose gets greater than the force to pull it downhill, it will come downhill. It will overcome the resistance caused by friction. The force in this downward direction against the slope is given by force equals mg theta, sine theta, where this, of course, is the weight of this object, straight down, W, and this is the sine of the angle of the slope. Sine, if you recall, goes like this, a sine wave. It begins out at 0 at a 0 angle and then goes up to, at a 90-degree angle, it goes up to the value of 1. So as this slope would come up to 90 degrees, it would basically be involving the entire weight of the object coming down. The coefficient would be 1. And of course, if that theta was like it is shown right here at 0 degrees, there is no sideways force. The sine of 0 is 0, and therefore there would be no force pulling it down. The condition here is that if the force pulling it down is equal to or greater than the static friction force that we explained in the last demonstration. If this force directed downward against the, parallel, to the slope, if it is equal to or greater than the force that is required to start it moving, known as static friction force, it will move. So let's show this in demonstration form. I have the block that I used in the last demonstration, and I have a mass, it's just to keep the two pressed together, 100 grams. So I've got a little over 100 grams here, and on the side, you cannot read it here, I can read the other side, is a protractor which measures angle. So I'm going to put the block up here. I'm going to clear the bottom of the ski slope, and I'm going to start raising this slightly. I'm up to 10 degrees, 15 degrees. I'm going to slow down. I'm up to 20 degrees, and it still hasn't overcome the sliding friction. I'm going to raise it up to, I'm almost there. The top weight is coming off. I'm at 23 degrees. And the whole thing slides down at 28 degrees. So I was at a 28-degree slope, and the stuff starts sliding down. You don't want to be in an avalanche like this. This is exactly what happens, except you have multiple planes. We're going to raise it up, and it will start sliding. At this point it's 25 degrees. I must have put it all over. The smoothness of this plank is not the same all the way along, unfortunately. Let's take this eraser, put the eraser on here. And I'm going to bring it up and measure what its angle of greatest, oh, there it is. It's only at about 23 degrees. 23 degrees. Let me see what else I have around here. Oh, big mass. I can experimentally determine that was only 22 degrees. So once I know this angle, and I know the mass, and I certainly know little g, I can find out what the force is pulling this down. I can just set it up there. I can tell the force pulling it down, and once I can tell that, and I know its mass, I can do a backwards calculation and get its coefficient of sliding friction. Or, as in most of the case, if you know the coefficient of sliding friction, and you can do the vector resolution here, this is nothing but a simple vector resolution problem. That's where sine comes into play. Then what you could do is tell how high you could pile a hill where this wouldn't slide down. So if you were building a highway and you needed to find out the angle of greatest repose for that highway on the slope on each side of the highway, you could do it that way. Of course, in the real world it gets more complicated because you're dealing with the cohesion between the particles in the material. You got grass growing on top, so that tends to keep it from slumping, and it absorbs the water and all that sort of thing. So, but in an ideal sense, you want to apply this equation. Thank you for seeing the demonstration.